So that all sounded pretty good. We had an equation that used the period that we measured to calculate how far out the planet was, r, and we had another equation that gave the radius of the orbit of the pulsar as it wobbled back and forth, allowed us from that to work out the mass. But there's a problem. So let's imagine we've got our pulsar, and it's going round in a little bitty circle because it's leaning back against the orbit of the planet. Now what we really want to know is R1, the radius of the little circle being done by the pulsar. But unfortunately, that is not exactly what we're measuring. Let's imagine the Earth's over this way. What we measure is that the pulsars come a little bit earlier or later because the pulsar is a bit closer or further away from us. So where is the pulsar at its closest? That would be at this point in the orbit, in which case its distance to the Earth is that. It's at its furthest over here. So what we measure, the amplitude of the oscillation in distance, is actually this value here, which I'll call R observed, not R1 at all. And if the orbit were perfectly edge-on, then R observed will be the same as R1. But if the orbit were incredibly tilted to the line of sight, in that case R observed can be much, much less than R1. And unfortunately, we have no way of knowing what this tilt is. All we see is that the distance oscillates, but whether it's oscillating a little bit because the orbit's edge-on, or oscillate a little bit because actually the oscillation is much bigger, but it's tilted to the line of sight, we have no way of telling. So let's try and calculate this effect. Let's imagine that the plane of the orbit is something like this, and we normally measure the angle of the plane of an orbit with what's called the inclination angle. So here's the direction to the Earth. We normally measure I, where I is the angle between the direction to the Earth and this vector, which is the axis of the orbit. So it's a line through the middle of the orbit at right angles to the orbit. It's, if you like, where the hinge would have to be if the orbit were a wheel, the axle of the hinge of the wheel. So if this is I, and this is R1, R observed is going to be here, that distance from there to there, because while the pulsar is moving from there to there, that's how much the distance along the line of sight towards the Earth, the distance to the Earth, changes. Now if we know this angle here is I, this angle there must be 90 degrees minus I. That's 90. The angles inside a triangle add up to 180. So this must be 180 minus 90 minus 90 minus I. So that must also be I. So then using trigonometry, if that is I, sine I equals opposite over hypotenuse. Opposite is up here, R observed. Hypotenuse is R1. So that allows us, if we knew sine I, to go from the observed to the actual orbital radius. Now if you remember that the mass of the big object over the mass of the small object, so the mass of the pulsar over the mass of the planet, is equal to R over R1 minus 1. Now normally R is much bigger than R1 because the mass of the star is much bigger than the planet, which means we can make the rather useful approximation and just cancel that one out because this is going to be so big that this is normally millions, so a million minus 1 and a million are pretty much the same thing. So in this case we end up with M2, which is the mass of the planet, so I'll call it mass of the planet, is equal to the mass of the neutron star, times R1 over R. But unfortunately, we don't know R1, all we know is R observed. So R1 equals R observed over sine I. So what we actually measure is MP sine I equals M neutron star R observed over R. So whenever you see mass of an exoplanet, what they're normally giving you is not the actual mass, but M sine I. If you look at the various online tables, you'll see they've got lists of M sine I values, not just M values. If the orbit is close to edge on, so I is near 90 degrees, then M sine I is going to be nearly 1, so that's about the same as the mass. But if the orbit is very edge on, like here, then I is small, sine I is very small, so the mass of the planet must be very large to compensate and give us the same observed signal. So it's a real ambiguity. We can't measure the mass, we can measure mass sine I. If we have a vast number of these things, then on average, they're going to be orientated in all directions. They're not all going to be pointing straight towards the Earth unless there's some great cosmic conspiracy. So for a large population, you can work out something on average. But for any individual object, you don't know the mass. All you know is M sine I. Bummer.